Okay, lesson 115. We're going to spend most of our time here talking about series circuits, introduction to series circuits. We're going to spend actually a couple chapters here discussing that, which will eventually lead into parallel circuits. But I think the first thing you got to wonder, you got to clarify is what is a series circuit versus what is a parallel circuit. So right away, here we see a series circuit. Here's a parallel. What's the difference? How do we know which is which? By definition, kind of the main thing in a series circuit, there's only one path of current flow. So there's only one place those electrons can flow to. The other way to look at it, if I'm to remove any one of these, so each R1, R2, R3 is a resistive element or a filament or some type of resistive load. If I'm to remove any one of those, this circuit is now incomplete because there's only one path for current to flow. So if I take R2 out of there, it's a broken circuit. Circuit's open, it's not going to work. But on a parallel, I have multiple paths of current flow. So you can see here current can go through the path for R1, for R2, for R3. If I'm going to take one of these out of here, if I take R1 out, R2 and R3 are still complete. Okay, so again, we're going to talk about series circuits here, so everything we're talking about is sort of this configuration here, right? And it doesn't always have to have three elements. It could have even one element is technically a series circuit, but it could have 2, 3, 4, or infinitely many. So we'll just throw that up here. So there's some rules we got to learn about for series circuits. We have a rule for every one of our electrical measurements: voltage, amperage, resistance, and wattage, right? So the voltage in a series circuit is what they're going to say that's additive, okay? And the way your textbook talks about this is each of these resistive loads, you're going to have voltage dropped across it. So in other words, if you're to take a voltage reading here and here, and if it, let's just say it's a 120 circuit, you're going to read 120 volts. But if you take a voltage reading from here to here, you're going to have less than 120, because essentially the way to think of it is some of that voltage has been used up. So each one of these resistive elements is going to use a certain portion of your voltage until there's none left at the end of the circuit. And when we look at an example, maybe that'll make a little more sense here, but keep that in the back of your mind for now. When it comes to amperage is equal anywhere in the circuit. No matter where I take an amperage reading, it's going to be the same. Why? Well, quite simply, there's only one place for that amperage to flow, so it all has to flow through the same path, right? There's no other path where more or less amperage can flow through. Resistance is going to be additive, and that's simply the fact of each one of these resistors or loads has a certain resistance to it. Our current has to flow through all of them. Again, there's only one path, so it all adds up to make your total resistance additive in this case. And wattage is just going to be additive. That's the same for series or parallel. Just remember, wattage is electrical work. So this does some work, that does some work, that does some work, add them all together, that's what the circuit does. That's not going to change from series or parallel. But there's kind of a fifth rule, and that is Ohm's law. So between these these four rules plus Ohm's law, we can find out anything we want about any of these resistive elements, the circuit as a whole, if we use them in sort of the right order and with the right approach. So let's throw an example up here. This one actually comes right out of your textbook. So the first one we're going to look at is just a two-element circuit, right? We have element 1, which is here, element 2, which is here. They're equally rated, okay? So they tell us in your textbook these elements are rated to deliver 1200 watts of heat. This is a water heater, by the way. 1200 watts of heat at 130 volts. So the first thing I'm going to tell you about a series circuit is rarely are you going to find, especially on these textbooks problems, that you're operating them at their rated voltage. Rarely does that happen. So hopefully that sounds familiar. What do we do when we have something operating at a different voltage than its normal rated voltage? Well, hopefully you guys all said find the fixed resistance using Ohm's law. Does that ring a bell? Because it should. So if we remember, the only property that's not going to change about a resistive load is its fixed resistance. No matter what voltage we apply to it, its resistance will be the same. So let's use its rated values to find resistance here. And the nice part about doing a problem where both elements are the same, or all the elements are the same, you only have to do the calculation once, and we can apply it to both loads here. So Ohm's law tells me E squared divided by P equals R. So specifically in this case, 130 volts squared divided by 1200 watts. it's going to equal R, which that is 14.083 ohms. So the fixed resistance of either of these elements is 14.083 ohms. Okay, so we're going to table this 14.03 ohms over here with our rules. We'll need to bring that up a little bit later. So as soon as my slide catches up here, it'll bring up my table here. But I like to create kind of a little table or a little chart. Okay, so you'll see along the left hand side we have a row for voltage, we have a row for amperage, row for resistance, and a row for wattage. Now I have a column for element number 1, I have a column for element number 2, and I have a column for total, or the total circuit. Okay, so what I want to look at here, what can we fill in right off the bat? What do we know here? Something I haven't said yet, but they always have to give you, is your total voltage. What is the circuit's voltage that you're connecting this thing to? And they tell us in the textbook it's 240. So whatever your circuit voltage is that you're actually connecting to, that's what goes in your total voltage section here. So that's always going to be kind of like your free space, right? So what else do we know right off the bat? Well, we figured out the resistance of each of these elements is 14.083. So let's go ahead and plug that in. Again, since they're both the same, we only have to do the calculation once. But we know resistance of each of element 1 is 14.083, and the same for element number 2. Now, this is where we're going to have to rely on these new rules that we just talked about. So what do we know about the total resistance of a circuit, right? We know that it's equal to R1 plus R2. So I can now take R1 plus R2, and that's going to give me 28.166 ohms, right? So what we've been doing is working towards a spot where we have two values in any one column. Why is that important? Well, quite simply, Ohm's law, right? If I know two values, I can find the other two values. So I know E, I know R. I want to find I in this case, and I'll tell you why in a minute. So Ohm's law tells me if I have E and I have R, I can take E divided by R equals I, right? So 240 volts divided by 28.166 ohms equals 8.521 amps. Okay. Why do I want to find I? Why is that important? Whenever you guys are figuring this out, find I as soon as you can, and here's why. I is equal anywhere in the circuit. So my total amperage can be equal to amperage of element 2, amperage of element 1. I just filled in that whole row in one step essentially, right? So now hopefully you're seeing a pattern here. I've got two values in these columns as well, right? So what does that mean? It means I can use Ohm's law to solve for the values I don't yet have, right? So again, we have I, we have R. I'm going to find E here. I could do it either way. It doesn't really matter. But if I want to find E, Ohm's law tells me I times R equals E. So in this case, 8.521 times 14.083 equals 120. I know if you actually do the math, it's slightly off, but trust me, that's a rounding error. You're going to see a lot of little slight discrepancies due to rounding, but we just kind of have to accept that at this point. So again, I found voltage of one element. These are equal, so I don't have to do it twice. I can simply fill them both in, right? And now what do we do? Well, at this point, we have three values in any column. The only thing we can do is use some Ohm's law here. And I could really do this for any of these columns. It doesn't really matter. But in this case, I need to find P. Let's look at column 1 here, element 1. If I use Ohm's law, I've got a couple options. I'm going to go with E times I equals P. 120 volts times 8.521 amps equals 1022.52 watts. Okay, again, I can fill in both those columns. Now, I could use Ohm's law here, but I'm going to take a little different approach. What do I know about the total power in a circuit, the total wattage? Well, I know P total equals P1 plus P2. So P1 plus P2 equals P total, right? So we just solve for everything in this circuit here. And let's take a step back, let's think about it. Does it make sense? We can really do a lot of checks with this chart. I know that the total voltage should be E1 plus E2. Well, 120 plus 120 equals 240. There you go. Another little check we can sort of do for ourselves. If I fed this element at 130 volts, I'd get 1200 watts. I'm actually feeding it at 120 volts, a little bit less. So we know that I should get a little bit less wattage out of that element as well. And we check, and what do you know? I do. 1022 versus 1200. So it all seems to add up. It all seems to make sense. So again, we have nice checks and balances here all along the way. The other thing to point out, whenever you have equally rated elements, all equally rated, there's really no need to calculate your voltage. You can take your total circuit voltage divided by the number of elements. So in this case, 240 divided by 2 elements equals, of course, 120. That's only going to work if you have all equally rated elements. Other than that, we're going to have to kind of do it the way we showed here, right? So let's look at an example. I want to look at another one. We're going to have 3 elements, and they're not going to be equally rated. So not really any different. It's just not quite as convenient, right? So again, we're just kind of base it off this sort of diagram up here. What do we know about these elements? Well, let's check it out here. Element number 1, let's say, is rated 60 watts at 120 volts. Element 2, 0.625 amps at 120 volts. And element number 3, 100 watts at 120 volts. And you'll notice here, you know, this one's wattage, this one's amperage, that one's wattage. It doesn't matter, because we're going to find fixed resistance either way, right? So right off the bat, I'm going to tell you we're going to operate this thing at 120 volts. So we can fill that in. That's kind of like your free space. They have to tell you. So we're connecting to a 120 volt circuit. So we got that. Next, we're going to find fixed resistance of each element using Ohm's law. And I won't drag you through all the details, but if we use Ohm's law to do that, we should get 240 ohms for element 1. We should get 192 ohms for element 2, 144 ohms for element number 3. So we can throw those values right in our table down here, right? And just like last time, we can find our total simply by adding all these up according to our resistance rule for series circuits. So we go ahead and do that. We get 576 ohms total. Next, hopefully you guys are jumping ahead. I'm going to find that amperage because I can carry that straight across. So I'm going to use Ohm's law, and that's going to tell me 120 volts divided by 576 ohms equals 0.208. And of course, I know according to my amperage rule for series circuits, I can throw that right across there, no problem. Okay, now, and again, hopefully this is looking familiar. I'm going to go ahead and find our voltage, because we have 2 values in every column, so I can use Ohm's law to find whatever I want at this point. I'm going to go with voltage. You don't have to do this. This is just sort of the order I like to do it in. So Ohm's law tells us amps times ohms equals volts. So we have amps times ohms equals volts. Same story over here. Amps times ohms equals volts. And third time. And if you go through and add these up, again, barring any rounding errors, we're within much less than 1 volt of 120. We can do our check. E1 plus E2 plus E3 better equal 120, or really close to it. And if you check that we're 119 and some change, if I remember correctly. Again, that's just rounding errors while we're off there. So we sort of have one more piece to fill in here. And again, it should look very familiar. What do we do there? So yeah, in this case, we're just going to use some Ohm's law. We're going to take volts times amps equals watts. All right. Again, we'll do volts times amps equals watts. Volts times amps equals watts one more time. And again, you could use Ohm's law again if you wanted to. I'm going to choose to use our our wattage formula here to fill in our total wattage. We're just going to add them all across, and there you have it. I believe if you actually did an Ohm's law here, again, you come up with a slightly different answer. But again, at this point, if we're all within one whole number, we have to call it close enough because there's a lot of rounding that goes on here. The last piece I'll leave you guys with, speaking of rounding, I think we mentioned we want to round to within 3 decimal points. I think if we all do that across the board, it keeps a nice consistency. I know we're still going to have some discrepancies, but again, we can all get within the same ballpark anyway. So again, keep that in mind. Keep these 4 rules in mind. Don't forget about Ohm's law, and most importantly, when you're starting any of these guys, find fixed resistance right off the bat. Don't even think about it. Just jump to it. Okay? So spend some time with this. Practice all the problems. This is going to come up over the next couple chapters, and then we'll build into parallel circuits and eventually combination as well.